Okay. Well, it's a pleasure to have here today Ramses Mena from Universidad Nacional, Autonoma de Mexico.
Good.
He's actually the president of the Statistical Association of Mexico, right?
Good.
And I had the chance to meet him at different in multiple international conferences. He was the program chair of the International Society of Bayesian Analysis. He has different positions in the profession. So today he's going to talk to us about decreasing weights, Bayesian parametric initial models, and their applications. Thanks for coming.
Well, thanks, Michele, and thanks everyone for being here. As Michele was saying, I met him a long time ago in Italy, but he doesn't want to say how long I met him first. So he goes back to the previous BMP, right? Which is nothing.
I think that's at the same time.
It was 2005 probably.
Yeah.
Anyhow, the story I'm going to tell you about today is a war that's been going on for a few years. It's a simple idea that started with Stephen Walker and Ruth Fuentes, and then other collaborators jump in for other extensions of it. But the idea is something that goes into the line of making things simpler than complicated, right? So let's it is. It's not working. What happened? Okay, I'll do it like this. So suppose we observe the following data set, right? So we're all statisticians, and the first thing that comes into mind is, well, I know this is not like very nice distribution, so let's put a prior, let's put a Dirichlet process, mixture process, and then try to fix something over there. Or let's try, for some others that have a bit more knowledge of it, say something more complicated, like a mixture of normalizing inverse Gaussian. I put my models here, right? A mixture of less gamma. But all of them pretty much look the same, right? In a way. So in a way, they all give you like a nice estimation of the density of that histogram. All of these results come from a convergent, typically a convergent state of a Markov chain Monte Carlo that runs in a state space of densities that we are used to in the Bayesian Nonparametric literature. So the idea is that if you ever touch one of these things, these kind of estimates are really sensible to hyperparameter specifications, either in the kernel or in the prior guess at the shape of the nonparametric model, or the randomization of the random probability measure as well, which is, for instance, in the Dirichlet process, for those who know what the Dirichlet process is, to put a prior on the mass parameter, or the techniques you use to attain convergence in the Monte Carlo process. So there was a long story, like started probably 20 years ago, about making the models a bit more complicated. What's going on with the Dirichlet process? That all these things, we need to accelerate the process, we need to randomize things to make it work. What is going on? So probably the support of the Dirichlet process is not good enough. So why don't we try to make it a bit more complicated? To make it, that was the idea, to make it a bit more robust. And by making it more robust, it became more complicated. So the problem is that when you make things complicated, computationally speaking, then it comes with a cost, right? It comes with a cost, and sometimes that's not always feasible. So what I'm going to talk about today is a different class of random probability measures. Not many of you already know, but you don't know, you know. So, okay. So, and the idea is that this simplistic way of doing things solves the same problem without compromising the good thing of Bayesian nonparametrics. And for doing that, come on, Michele. Yeah, there you are. No, this is going back. So from here, it listens to me, but the other way around. Okay. Anyhow, so I have a plan, and Michele told me that there will be some students here. So I will speak a bit about Bayesian nonparametrics, what it is, is my view of it, right, of Bayesian nonparametrics. And then I go to the special topic of the talk, which is these models I'm talking about, and of that we call order weight priors. And then I'll speak about some applications. So everything starts with a random phenomena, typically when we are in statistics. A set of observations that represent a higher population that we cannot sample, we cannot sense completely, or just something that we cannot replicate easily, right? or whatever you can imagine as a random phenomena. There are many ways to think about the process of random phenomena. There is like the way to explain the random phenomena. There is like this philosophy that I'm going to explain here is not the only one, but it's one of the approaches that look at it in a nice way, and it serves to justify Bayesian Nonparametrics pretty much. So you have the random uncertainty and the epistemic uncertainty. As the name says, the epistemic uncertainty is the one I can learn with more information, and the random uncertainty is the intrinsic nature of the event I'm measuring that is difficult to capture with data. Okay, so historically speaking, this is the idea that goes. I mean, there is a lot of philosophy, and I'm going to go into that. But the idea is that you have this random phenomena, you have data, and with this data, you can make inferences about the epistemic uncertainty. Okay, so you get data and you learn. So you might be thinking now, epistemic means, okay, so it's going to be represented with a parameter. So with more data, I learn about the parameter. And you can tell, well, random uncertainty is going to be the model. I choose the normal distribution, or the gamma, whatever, right? And that, once you fix that, you can move that. Or if you want to be wider, you can choose a mixture of these processes, but it's the same idea, right? So there's a nice paper by Goldstein about that you can read about. So, it's going backwards. This is weird. Am I holding it?
Holding it, yeah.
Oh, well, that is why. So essentially, there is a basic setup. The basic setup is, in statistics, is the more information we have, the better quantification of uncertainty we have. Okay, and the better induction, the better statistical induction about the random phenomena we are studying, we can realize. So, of course, there is a very important point, and the very important point is that realization of a phenomenon in probability is encoded to random variables, typically. No, it's not like that. Come on, the pointer is here. Okay? So, can't do the pointer like that. So, the realization of the random phenomena are encoded into random variables. Okay? These random variables represent the thing we are going to study, and this is where the statistical idea comes back. Logical or physical independence does not necessarily imply stochastic independence. And that's precisely where Bayesian Nonparametrics come from. In order to learn statistically speaking, probabilistically speaking, about a random phenomena, even if the random phenomena is physically independent, we need a stochastic dependence. Otherwise, we don't learn, right? If we have these kind of things, like we do, for instance, in IID assumptions on the statistical model, we don't learn about the phenomena, about the physically independent phenomena, say. So, statistical learning requires a stochastic dependence. Otherwise, we don't learn, right? So that's what some people like to justify Bayesian Nonparametrics. Under physical independence, all we can say about the stochastic modeling these random variables is that they have certain symmetry. Okay? I mean, the law of the random variables, the subsequence of the random variables, has certain symmetry. That's all we can say under physically independent phenomena. So we don't have time dependence, we don't have whatever dependence. It's just physically independent phenomena. So this is going to be clear. This is really nice. So I will go like that, because otherwise I will go mess with this. So symmetry, stability principles are the base of many theories, either in statistics or in probability, right? So essentially, the law of the random variables have certain replication. The past and the future have certain similitude. So there is a principle that goes back to the philosophers Hume in 1740s, okay? That says like you have the uniformity principle, right? Essentially, you are able to replicate somehow what you observe, and that's the whole way to justify induction, statistical induction. So the major symmetries in statistics we are used to it is like IID, statistical symmetries. We have exchangeability, we have stationarity, and I think we're going to talk about exchangeability, this topic, but of course stationarity is a very interesting topic as well to talk about. We probably speak about towards the end of the talk. So there was this quote: "Practitioners seem to prefer the language of populations, theoreticians that of exchangeability," by Lindley, right? So anyhow, so we have exchangeability sequence. What is exchangeable sequence? For those that are not familiar with the concept, is essentially the law of the random variables that represent my random phenomena are invariant under the way I sample them, okay? So are invariant, if you want to put it in other terms, under this permutation of the indexes, if you want to think like that. But it's the way a sample, the way obtained information is invariant. Okay, the law of that remains invariant. So it makes sense with the physical independence kind of thing, right? It makes sense with that, and it's the basic one. So, what can be the question is, what can we say if we depart from here? Of course, this is a very quick way to justify exchangeability. It goes a bit lower than that. We can say something about the law of that by only assuming this symmetry, and there is a very nice theorem by the Finetti that essentially tells us that this is possible. Okay, I did it all this time. So this is a bit theoretical, but it's not going to be like the whole of the talk. But think about this: the space of all this space here, the space of all possible probability measures, all possible distributions. Say, including the normal, the gamma, whatever. Okay, all the possible distributions in a particular space. This space X. Think about the real numbers. So think about all the possible. Do we have a pen here? No. Yeah, I do. So can I write here, or is it just the
Yes.
word? I don't want to do something that it's not that. So think about, this is the real line, and you have all the nice Gaussian distribution, but you have all the distributions. So you think of that space like being that pre-calligraphic, right? And then what exchangeability says is that a sequence of exchangeable random variables, a sequence of random variables is exchangeable if and only if there exists a quantity such that conditioning on that quantity P, you have, if you cover this, you have independence. So there exists a quantity that conditionally on that quantity, we obtain that independence, stochastic independence, okay? But that quantity is the whole topic of Bayesian nonparametrics. That quantity is the thing we have to learn with the data, because essentially that quantity can be seen as the law of the empirical distribution function, the law of the sample, say, right? So if we take the limit of this sample when n tends to infinity, then the limiting of this sequence is going to be that law that allows me to decompose the thing into independent random and identically distributed random variables. Okay, so that's the idea of Bayesian nonparametrics. Since anything, virtually anything, can be seen as the limit of empirical distribution functions, any distribution, so we need to model. So the Finetti tells us that this measure, this decomposition is unique, meaning the joint law of x1 to xn for any n can be decomposed like this, and this Q is unique. So if I give you a sequence of exchangeable random variables, for sure you have only one Q, only one measure on the whole possible space of measures. Okay, so that is giving you a unicity, but it doesn't tell you which one is it. And that's a problem. So you need to model, you need to put a prior, you need to learn about it. That's Bayesian nonparametrics. That's Bayesian statistics in general. So the unknown that allows us to disaggregate the elements of this exchangeable sequence is random. That quantity is random. That's also telling us this. This quantity is random, so it can take any value here, right? So essentially, we need to put a model on it. So the concept of exchangeability is like a very quick way to justify the existence of a prior. You need to put a prior on that quantity. Okay, so what's going on with this, right? So essentially, I will do this. So there is a bijection. I have the joint law and I have Q. So a nice way to construct a model is I give you the law of Q. Think of the normal distribution. Now very simple. I give you this sequence of IID random variables with are normally distributed with mean unknown. But the mean has a prior normal. So if I integrate that normal, then I have a exchangeable sequence, okay? But that exchangeable sequence, I give you first who's Q, and then you get the joint. But it can be the other way around. I can give you who is the joint which is the joint distribution, and if that joint distribution genuinely corresponds to an exchangeable random variable, then you obtain only one Q, okay? So this is what I was saying. So probabilistic speaking, if you want to think about it, the Bayesian approach is equivalent to the assumption of exchangeability on the physically independent observations. And that's a concept that goes back to the Finetti, and there was a lot of philosophy behind that discussion about this idea of to justify Bayesian analysis. Not the only way to justify Bayesian analysis, but this is the one that goes along with the Finetti. So of course, once you have the sequence, the exchangeable sequence and its law, you can always find the predictive distribution, which is essentially applying the probability rules here, the law of all of the elements divided by the law of these ones, whenever that exists, okay? That this quantity can be seen as the expectation of this predictive distribution, this posterior distribution, okay? And that's the way we usually do in Bayesian analysis, and it's equally possible to be done here. There is a detail in mathematics that does not allow you to have this quantity all the time, because we cannot always have dominated case in functional spaces, but the idea is the same. So what is going on? What is going on with exchangeability? If that measure Q, that is called the Finetti measure, the Finetti measure characterizing the law of the exchangeable sequence, if that measure degenerates in a particular Q theta, okay, then the law of this exchangeable sequence is only the law of an IID exchangeable random variables. So exchangeability includes IID as a particular case when the Finetti measure is degenerated in a particular point, in that point, right? Imagine this circle here is the space of all possible distribution. So the normal with parameters blah, theta, is just one point there, okay? So what else can I do? What else can I do? So if I degenerate the Q in a parametric family, let's say the parametric family of normal distributions with mean, mu, and variance sigma square, okay? I put, the Q puts mass 1 on those, then exchangeability becomes immediately this, where this normal, or this F distribution here, is just a parametric distribution. And this prior is the prior on mu and sigma, okay? So if I integrate mu and sigma, then I recover exchangeability. But that only covers this space, right? The space of the nicely behaved, very symmetric, very nicely normal distributions. So what is Bayesian nonparametrics about? Is about having a bigger space, an infinitely bigger, a space that is of cardinality infinite. So say we have the space of all distributions that are discrete, or the space of all distributions that are continuous, okay? So that space, of course, covers more or less, it depends if I include both or just the discrete ones, the space of all distributions on X. So that's the idea of Bayesian nonparametrics. And when is this going to happen? When I want to be, this is going to happen only in the case where this space X, the space where my random variables are taking values, is non-numerable, right, and infinite. So for instance, if I have here from 1 to 10, the problem is not considered non-parametric, although in a sense it's the same idea. So for instance, if this X here is 0, 1, I have tossing a coin, and the Finetti theory tells me that this here is just the Bernoulli random variable, right? Because the Bernoulli random variable gives theta to one parameter 0 and 1 minus theta to 1. So all the sets in X can be measured by one parameter. But what happened in the infinite case? You have plenty of them. You have a function, right? So that's going to happen. You have still, it's not, the name is very bad. It's not Bayesian nonparametrics. It should be Bayesian super full parametrics, because you have an infinite function, right? And something that is infinite. So that's what happens when this is infinite.
I like to use the word richly parametric.
Exactly, richly parametric, probably. So essentially, what happens if this is not an infinite nature? What we have done in a basic course on Bayesian nonparametrics is we degenerate this space in the space of normals. We have a model, and we do Bayesian visual Bayesian statistics, obtaining a posterior distribution. But if we want models giving a positive probability to all the elements in that big space, okay, what can we do? How can we construct this kind of models? Okay, how can we construct these models? So that was the question that was somehow started in the 70s or even before with Friedman. And how can we construct models for this, right? Oops. So there are many approaches. I will just put some lines on this. So the basic approach to construct an infinite dimensional object is to take an infinite dimensional object and transform it into something that I like. So that's what people has done in most cases, which is, what about if I have a process that looks like this? And for those who have taken a Bayesian basic course in probability or in stochastic processes, it's like a Poisson, compound Poisson process, right? So what about if that compound process somehow is truncated here, that this pretty much looks like what? Like a CDF of a discrete distribution. But of course, if I replicate another another trajectory of that, then you have a different sort of thing. And actually, we can prove that under certain conditions, the trajectories of this process tessellate or cover the whole space. So essentially, I can take one of these processes, transform it into something that looks like a CDF, or if the process is continuous, like a Gaussian or a Gaussian process. If the process is continuous, the trajectory, say, of a diffusion process, I can transform this into something that looks like this. Okay? So that's the idea that most people have used for constructing priors, which is the transformation of the process. But of course, there are many other ideas that goes into the finite dimensional distributions with specified the Kolmogorov's construction of process, right? You have the normal distribution in dimension 10 dimensions, but if you want to go to infinity, you see that this is projective, and then apply the representation theorem of Kolmogorov, and then you have an infinite dimensional space whose finite dimensional distributions become to that, and then that's the finite dimensional approach. And of course, I'm putting in red these two ones here, which is the one that I'm going to use. You have Polya trees, which I'm sure you know all about because we have some of the names here. So, but the idea is very simple. The idea that I like the most is the idea that goes into I just replicate that because it's going to help me to understand the simplicity of what we are doing. That the idea that we use the most is the idea of transforming a process like this. That is a process called completely random measures. So a completely random measure, if you want to think about easily, think of this process, okay? But think of this process like the compound Poisson process with infinite jumps, not necessarily compound Poisson, but think of this process instead of being in the real line in any space. And that's a completely random measure. A jump process in a bigger space, right? So if you take that process that is a measure mu, that if you apply this measure mu in any partition of X, or for any couple of sets of these independent sets, then the random variables are independent. That's the definition of completely random measures. In other words, the property, if you want to think about independence of increments when we study stochastic processes, is the same as the completely random measures. It boils down to that property in one dimension, okay? In many dimensions, it's called completely random measures. So of course, there is an example of the Poisson process, of when you have a Poisson random measure, if you want to call it like this. So you have a Poisson measure, meaning that the distribution of this random variable is Poisson with a particular mean. And that mean has to have certain properties, okay? And of course, there is a very nice theory by Kickman in the 60s, and that you can check his book on Poisson processes on 93, which is a very nice book. It's very easy to read for everyone. It doesn't necessarily need to be a mathematician. And then and tells you that the composition of completely random measures can be done in this kind of style. So they are discrete, discarding the non-Poissonian case, the continuous case, and then you have these two components. One component is jumps in a fixed number of points. So you have the fixed number of jumps, and the other component is the completely unpredictable jumps. So what's going to happen, what happens typically in applying theory, in every theory you apply, is you assume a model in this as a prior, and once you observe, this is what you observe, and you put the model in those particular fixed points. So the sample is going to be in the points. So there is a very nice point here. So what's the point of using this? Let's go back a bit. What is the point of using this? That I know the law of this, okay? And for any process like this, if I know the law of this, then I can do something that at the time I transform, then I know the law, and that becomes the law of Q, the law of the Finetti measure. So essentially, the law of this can be studied through this Laplace functional. Remember, the way to study the law when it's very difficult is to apply a transform, like Laplace transform or whatever. So this is the easiest way. Of course, when you really do it, you realize that there are other transforms that are easier to deal with, like Stieltjes transform or something like that. And there are many examples. So there are many examples when I choose this mean of the Poisson random measure to be like this, that can be decomposed like independent, say, like this. There are many examples, right? And there are other examples when this cannot be decomposed and independent. We are not going to talk about those. But this particular example, for instance, is the example that gives us the gamma random variable. So a gamma random variable can be decomposed. It can be is an infinitely divisible random variable with infinite activity. I always like to talk about this because people always get confused. And the point, all you need is the integral from 0 to epsilon, okay? The jump from 0 to epsilon, whichever epsilon is little, I mean how little epsilon gets, of this, what is it? E to the minus, just to use the same notation, tau. Tau, what is this integral? Everyone can do it very quickly, right? Because of the 0, this becomes infinity, right? So you have an infinite number of very small jumps. So a compound Poisson does not fall into this class because the compound Poisson has to be finite, this thing, right? So it's a bit different than that. It's the case with infinite activity, they call it, and all of these models have infinite activity. So the story that happens in the early 2000s or late 90s was how to extend the Dirichlet process construction by assuming different priors on this. And this completely changed the story. We have a lot of models that with Italians, Igor and Antonio, we sort of went into those and tried to develop models for that. I was part of that story as well. So the idea is that you have this random probability measure, which is composed as a normalization of a completely random measure. Of course, if you normalize with the same factor here, which is the law in all the space, the property of independent increments, the property of complete randomness, goes away. So the nice characteristic of the law goes away. And then it becomes difficult to study the law. And then there are many approaches. If you want to learn a bit about it, you can look at these papers, and that's how they tell you how to sample a posteriori of these values, even when that is the case. But the point that I want you to grasp here is normalization comes with a cost. The cost is I lose the nice property of completely randomness or independent increments on this process, if you want to think in the real line. When you study that, since I explained, don't look at this. This is just math. So, but since you have a discrete sample, and this measure here, I go back. This measure here is discrete. It puts positive mass to ties, meaning a sample of size n can be decomposed into a smaller sample, which represents several values of that. So the probability of having two values the same is positive. So there are ties, and that obliges the sample to be decomposed in a small sample. So since these measures all are discrete, a way to study the measure is through the so-called EPPF, that is just a distribution on partitions. So I have a sample of size n, and I decompose that sample of size n in k groups, each group with n1 up to nk individuals. By choosing an exchangeable sequence and say Q follows a Dirichlet process or Q follows a whatever measure that I constructed, then I have implicitly a law, this law, on these random variables, on this space, on the space of partitions. A space of partition is a very huge space. It's a space finite for n, but it's very huge, right? So anyhow, so there is a lot of story behind this, very nice, because all the measures, all the discrete, almost surely discrete random probability measures, the study of those falls into study these quantities here. Once you have this, you define everything for the quantity, okay? And once I have that, for instance, the predicted distribution is just the same as we use for the Dirichlet, just that the weights change, right? The weights here, for instance, are in terms of this EPPF function, which is the probability of something new, is one group new, and this is one value, or the probability of picking one of the old ones is just putting another value into one of the old ones, all right? So it's very easy to see how that takes into action. So in the case of the Dirichlet process, we know the maths, and the maths are reduced to the typical weights of the Chinese restaurant, okay? Which are very easy because they are very nice fractions. But there are other cases I deleted from this presentation. There are other cases where this quantity, all the other cases that can be normalized, for this quantity gets something nasty. Something nasty here that then needs to be coded into the predicted distribution and is expensive computational. At the time I did it, we did it with using arbitrary precision packages, but it took hours to fix the galaxy data, right? I don't remember. Okay. Nowadays, of course, that's not something we can afford, right? So another way to understand random probability measures is the simplest. discrete random probability measures. Any discrete random probability you can think about can be seen like this. For instance, the Poisson distribution. How can you describe the Poisson distribution like this? The Poisson distributions on the Borel, on the countable set. So this set 1 is 1, 2, 3, 4, 5, okay? The integer set. And W is the weight that the Poisson distribution gives to 1, 2, 3, 4, 5. So the Poisson distribution can be decomposed like that. Any discrete, the negative binomial, the binomial distribution, the geometric. Any distribution like discrete can be decomposed like that. So if my starting point is from that, and I say, well, the weights and the locations are going to be random, then I have a random probability measure. That's a concept that is better than the other one, right? Because it's very quick. Come on, I just start from a discrete distribution, and then randomize the weights. I can picture many ways to do that, and randomize the locations. I can also do that in many ways. And then I have a random probability measure. Of course, you have to study the properties of that random probability measure. It has full support, blah, blah. So the typical example we use is the stick breaking weights. So we have to ensure that this happens, because now, since they are random, they have to add up to 1 almost surely, right? So the probability of that happening has to be 1, okay? So essentially, one way to do that is to construct the weights through the so-called stick breaking mechanism, which is essentially one of the ways to construct the stick breaking weights is with these sticks, well, these bits, these weights here, these being independent, for instance, right? So all you need is to ensure this is happening, right? They don't need to be independent, by the way. You can have something dependent in order to have something. But then you need to have this. This is a construction that is very nice in application because it's telling us how to do things. So theorem in 94 proves that if this construction here of stick breaking weights, I replace these B's with this beta distribution, then I recover the Dirichlet process. So a process that is a normalized gamma process, okay? So actually, the same Ferguson in 73 proves two constructions, right? So the story we know, and there are many models for Q, but the points I want to make is normalization destroys completely randomness, and the first question that comes into mind, is there a class of processes like the complete random measures that covers the process once it's normalized? Once I normalize, is there a class of process like that? In fact, there is a very old problem, right? And the old problem was like this. It's a bit more theoretical, but I will stop with the theory here. The problem is that what happens when you mix a Poisson, think of a Poisson process, the easiest Poisson process you can think of, depending of your background, right? But think of a process that you use for risk theory and to compute the risk formula, right? So you have a Poisson process with a rate lambda. What happens if you mix over lambda? If lambda is random, and then you integrate that process. Then you destroy the independent increment properties of the Poisson process. But the resulting process is going to have exchangeable increments. So that's the idea, okay? As simple as that. And Bullman in the 60s pictured it like that in the very general way and say, look, what if you have a process like a Levy process, like the extension of a Poisson process, right? And then mix over the unknown. Of course, you're going to have you destroy the independent increment properties, but then you have exchangeable increment properties. That's getting very complicated, you're saying, right? Because now I have exchangeable increment processes, right? So you'll see that it's actually easier. So this is the representation that Bullman did, which essentially just quickly tells you that it's a drift, a Brownian bridge, and the stick breaking. Okay? The steam breaking, guys, is going to fall here. So all exchangeable random measures have this representation. Okay? So we know how to construct them. I know how to construct a very nice process, right? By stick breaking. We know not all stick breakings can be constructed by normalization, right? We have, for instance, the Poisson-Dirichlet process that cannot be constructed as a normalization, but it falls into this class. So this is precisely the point that I'm going to talk about today in the next slides. How much time do you have? Tell me I'm not. I still have 1 hour.
10 minutes, 15 minutes.
15.
15.
Ah, wow. It's going to be very quick. So the point is, one of the ways to construct, he's cheating, right? He's cheating, right?
No,
You're cheating, right? I will put my watch.
you really have one
Cheating,
right?
Anyway, it's going to go quick here. Because the point here is, the easiest way to construct this measure, this exchangeable random measure, is this one. And you're going to like this. think of the empirical measure and take the expectation, putting a prior on n. Whichever the prior. So you tell me, that story is old. I mean, old people did it in the 70s. Yeah, they were doing Bayesian nonparametrics without knowing that, right? So essentially, if you do that, you have this kind of model here, okay? And then you recover the whole exchangeable random measure. And the support of this, all the talk I'm talking, I'm not going into the maths, is full. We are not compromising anything of the support of the Dirichlet process, right? By doing this. So of course we know we can do mixtures if we have continuous data. I skip that. And we can do the posterior of a partition that is a mess because we have a big number of that, and then a prior on the posterior on the number of components. That's the way to do inference in the typical case of Bayesian nonparametrics. And I can do the estimation of the plots you saw at the beginning are using an MCMC for this, right? I skip this. So for big N, you cannot do computations. Actually, for n bigger than 15, it's very difficult to do computations because the Bell number of 15 is massively huge, computed in Maple, right? So for 10, for instance, for 10 samples, you have 100 and something thousand ways to do groups, for 10 groups, for 10 people, sorry, for 10 elements of n equals 10, right? You have 100 and something. If you have n equals 20, you have millions, right? So you need MCMC methods. The easiest method that I can think of, and we will present it because I will use it later on, is this one. So you have the slice method of Stephen Walker in 2007. What he says, look, you have this infinite representation. Since we cannot put in a computer infinite there, why don't we truncate? But let's truncate randomly, not just put in a number. How we can truncate randomly? By introducing a uniform random variable, okay, that allows you to truncate the weights. So when I have the Young distribution, if I integrate this uniform random variable, then I recover that. Given the set of weights such that this quantity is positive, this set is finite always, all the time. So conditioning, I have something finite. So that's the way we Bayesians resolve infinite problems. We condition on something to make it finite and work with it, right? So we have this very nice model here, and this is the model that is going to fall into that class. This set here is the set of all, it's a random set that is constructed by the random weights of the random distribution here, whichever it is. This, for instance, right? So, and then we construct estimations, and we do that. So now the topic of the talk from the last, accordingly with Michele, 10 minutes, which is very simple. So we know when we do Bayesian nonparametrics, so when we do mixture models, one of the main problems of mixture models is identifiability. What happened with identifiability? The likelihood of n observations, which each observation is modeled to a mixture model, the likelihood of that is invariant to permutations of the indexes, permutation of the way I messed up with these things here. So of course there are many optimal solutions, and that's a mess. Because if we allow the ways to be completely messy, that's the point of making a mess. So in this, again, going back to the 90s, there were a lot of PhDs spent of how to solve this problem by putting constraint on the thetas, by putting constraint on the W's, by applying Metropolis. What were you teaching just now? Reversible jump processes. So this is the realization. This is 100 iterations of an estimation of the Dirichlet process after 10,000 born-in iterations, okay? So this is 100 iterations. And you can tell, sometimes he goes wild because he doesn't know which ones to pick. There is an identifiability problem. It's called the label switching when it comes to MCMC, right? Yeah. So these are the weights, for instance, of the Dirichlet process. They are not necessarily ordered. They don't satisfy this constraint. So a way to impose very nicely the identifiability constraint is to put weight on the weight, to put an order on the weights. But how can we do that without compromising the randomness and the support? I mean, still we want to be Bayesian nonparametrics. So this is the idea that Stephen Rudd and I came up with some years ago. So take the Dirichlet process. The problem with the Dirichlet process is you have an infinite number of betas as a source of randomness. And actually, when you apply it, you have to randomize the total mass, because otherwise it doesn't fit. So what if we just take the expectation of those weights, okay? The expectation of those weights we know is geometric with these parameters here. And instead of putting a prior on the total mass parameter, we would put a prior on the lambda, this reformulation. So the model that comes out here, that we call the geometric process, is a model that, of course, the weights are geometric, so they are decaying all the time, okay? That solves the identifiability problem. It does not compromise the support. BCD, Ongaro, and other people proved it in 2009, I think, after we did a paper somewhere. And it's very simple because instead of having an infinite number of betas, we only have one, okay? So this is the first, instead of 10,000 born in, then 100, these are the first 100 iterations, of a mixture model, right? The same mixture model. So you can see how they actually adapt because you don't have that identifiability problem. And I invite you to test this in any process you have because it's very simple. When it comes to density estimation, this is the model to use. And the way I explain it to other people is this one. Think of a normal distribution on the real line. The real line is something infinite, right? I put a normal distribution, it's very nice. But I could put something different. I could put a T distribution. You have heavier. I could put a hyperbolic geometric distribution, right? It can be very complicated, like the Dirichlet, or it can be very easy as like the normal distribution. The same in the infinite dimensional space. It can be very simple as the geometric, and it can be very difficult as the Dirichlet or other distributions we were looking at. Okay. Of course, there is a compromise. I mean, everything comes with a price, right? So I will explain quickly why is that this works very well. So essentially, in the DP weights, the set that we condition in that slice method, so the idea came out when we were looking at the slice method. So we use the slice method to construct a new family, right? So this set in the Dirichlet is like 2, 5, 16. I mean, they have gaps. And that's for all of those who are actually apply the Dirichlet process, you realize that the labels suddenly have a very huge value, right? And that's what causes the label switching. So why instead of doing that, we just put 1, 2, 3, 4, 5, 6, 6? I mean, it's just a label, right? We don't compromise anything. And sometimes we do it, actually. We cheat and we do it in the computer, so it doesn't have any problem. But we are changing the model, right? We are changing to one of the geometric models. So if we do that, we put the set is 1 to n instead of any random set. And we put a prior on n. If we put a prior on n, then we come back to the empirical distribution function with a prior on n, okay? And that's the way to construct a very simple case of exchangeable random measures. So if you want to think of a different way, think of the typical way you construct random measures, but instead of having the stick breaking weights, you have these sort of weights, which are the tail mean measures of this discrete distribution, whichever Qn is. So the negative and if I pick up this, if I pick this Qn a negative and mean distribution, the weights are horrible in terms of this in this Gauss hypermetric function. But if you take the value with n equals 2, then or r equals 2, then you get the geometric case. So the geometric case is a particular case when it comes with that, right? So this to catch up here, I speak about 5 minutes more. Okay. Yeah, 5 minutes. I'm done. So essentially, I have this distribution here, which is a nice distribution. I can compute the EPPF. The EPPF is a mess here. It's not easy. We have a paper with Stephen Walker, 2012, when we actually work on it, and then we realize it has the same kind of results. But the problem is that we need to integrate this quantity here. I mean, everything. If someone here has a very good idea how to do that, all you need to do is integrate this function here with respect to lambda. And lambda is a prior you want to put. Can be beta, can be anything, right? So, and it's telling you as well, these are the allocation variables. They have to be ordered. They have to be ordered in the geometric. There are 1, 2, 3, 4, 5. So these are the two explanations of the model, the geometric. So as far as the asymptotic behavior, for those who are really mathematical and they know a bit about the theory of the processes, a way to understand the processes is to understand the random variable of, you remember there were ties, right? So there were ties, how many ties? So how many distinct groups? That Kn has an asymptotic behavior as n goes to infinity. And that asymptotic behavior tells you a lot of the random probability measures. So in this case, if we change the prior, the story here tells you, if we change it, we pick the geometric case only, not the general case, only the geometric. And we change the prior for lambda. This is when the prior is a uniform. You recover this log n with this constant. If the prior has a different form here, then we recover a power of log n, and we go like that. Da, 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 da. So changing the prior of lambda, we recover different powers of log n passing through the Dirichlet process, right? So we have a way to recover what is done with the Dirichlet process in terms of pieces, but we are not as good as other models like was on Dirichlet process, right? And these are other examples. So this is just another distribution with different priors. So the blue is the geometric, and the red is the Dirichlet. The blue is the Dirichlet process. The red is the geometric, and all the black ones are with negative anomalies. So as you can tell, this is something we are not recovering with the Dirichlet process here. There is some failure there, but it's just an estimation, right? The importance is not the support. The support, they both are okay, Dirichlet and geometric. The point is that with a very few iterations, you can do the same estimation, right? And that helps a lot in my last two minutes example. In some of the models, for instance, if you want to put covariates, you make the weights, the lambdas depend on a logistic Gaussian process, and then you can do kind of a regression model here, like this, like a dependent MDP, but dependent geometric process. This is like a regression thing. This is our estimation of the regression with this model. We did a stochastic process, very nice. So we took the lambdas, instead of being the lambdas fixing, we make the lambdas dependent on time. So we constructed time-dependent random probability measures. And we put a very complicated thing. Well, it's not very complicated. It's just a beta distribution moving in time with this generator, which is the Wright-Fisher model. So if that moves with time, then the resulting, the nice thing about this construction is, and also it happens with the Dirichlet, it's not only this. If you just put a prior on the weight, a process on the weights, and that process on the weights is continuous, Markovian, and stationary, then the same conditions go into at the random measure level. So you can have a model like this where this lambda t are Wright-Fisher, and then you can just do estimation. So this is the hierarchical model if you want to see it. You have a time-dependent Ys, and the time-dependent Ys are going to be modeled by this geometric stick breaking process, as we call it that time. And this is the estimation, which I skip because, but it's, no, I still have some minutes. The estimation is very simple, right? So, okay, it's not very simple. So the estimation for those who are doing time-dependent measure value process, or any time-dependent anything, what you need to do estimation properly is the function that allows you to model the time change. So in a diffusion process, in a Markov process, that's the transition density. Okay? So if you know the transition density, then this estimation is very simple. If you don't know the transition density, then it's very nasty. So in the case of the Wright-Fisher model, the transition density is not very easy, but can be decomposed. Oops, I skipped. Can be decomposed in this way. Again, with the infinite sum, in red I put here. So I put again the slice method there to get rid of the infinite sum. Okay, that's a trick. And the rest is just the slice method that we do. This is the typical Kali, Stephen Walker, and Griffin condition. Okay, and then this is the likelihood of the model, the whole complete model, which is easy. So the only point you need is a transition. So there are many ways to obtain very nice Markov processes, but I wanted the process to be continuous and a diffusion, and I was obsessed with that at the time. Now I realize for applications that's something very silly to do. We have done something better things now with easier transitions. Anyhow, I keep going here because this is just a slice. So, oops, yeah, this is just a slice method. You have estimations like this, for instance. These are the observations. These are the observations, the black ones. The blue one is the mean of the mean functional. Remember here that you're talking about a random measure, right? So you have a random measure. When you talk about the expectation, for instance, this is random. So the mu here is going to be what? Random, right? It's an stochastic integral, this one, right? Where this is an exchangeable increment process in this case. So this is going to be random, and you estimate that. The distribution of this, there are a lot of people working on it in Italy, they love the mathematics behind, but the distribution of this is not easy, okay? I can tell you something, for instance, when this is a Dirichlet process, and the prior guess of the shape is Cauchy, this is Cauchy. So you forget about everything, right? But when this is normal, and when the prior guess of the shape is normal, this is not normal, and it gets really nasty. It gets more complicated. But still, you can do MCMC, and what I'm reporting there is the mean of that, in blue, the mean of the random variable, and the high posterior density estimates. So we have done a lot of applications with the geometric. I don't report them here because I knew I wouldn't have enough time. But if you want, I can send you out papers. For instance, we have done estimations of pollution. And it turns out that when you use the geometric process, it gets really, really fast to do the estimation, as you saw in that little example, one dimension. Sometimes I think one dimension is easy to explain a characteristic of a model. You don't need very complicated data when it comes, right? Of course, that doesn't say that you need complicated data to prove the usability properly, right? So there are quite a few papers. I point out something here. So there is there is a review in 2013, I think. I go a bit ahead. There is a review in this book by honor of Adrian Smith, is this one here, that I review a bit of the whole story of the geometric. But of course, that's up to 2013, and there is a work now with the Blasi Igor when we talk about the convergence of the different number of species as n goes to infinity, and that tells you a lot of the properties. I think that would be it.
Questions?
Yeah.
You mentioned label switching. Is there, I'm thinking about the geometric inference with the geometric stick breaking process, and would there be a version of that where, imagine you had what was essentially the largest mode or group or cluster in your data, and as an early stage of inference it became, you know, number 7 in the index order.
Yeah.
Right. Eventually you're going to want to move that to number 1. Do you need sort of explicit proposals?
That is right. That is right.
Swap the order.
That's a very nice question, because a lot of the people not using these models is the geometric is because of that, actually, because they say, well, it's difficult. You think of this. A priori, you're putting a prior that goes and gives very little weight to a lot of number of components. So there is a trade-off. In the prior you put on lambda, you have to indicate how far you want to go in the number of components. If you include it with a reasonably speaking in computer terms, reasonably high probability, then it will pick up. It won't be any problem. And actually, we have a minute here, just for question.
But do you like swap over, stochastically swap the ordering?
No, we don't. You don't swap the ordering. Actually, the model picks it, right?
You just trust it.
You just trust the model in getting it, and it's gonna get it. I have the experiment here, the decreasing, because that was one of the.
For how large?
Yeah, that's the
how
point.
many observations?
That's the point. That's the point. Let me show you something quick here. So, for instance, that was a. Oops. That was an example that we sort of devised at some point, right? Because we thought about it. We thought about the point of having a lot of. You start with the problem is it can be recast in these terms. You have a big number of groups. That's it.
Yeah.
And then the geometric distribution shops, computationally speaking, because it goes definitively, we know that doesn't matter, right? Shops at 10, and you have 20, you are doomed, right? Because you are not going to recover that. And that's the purpose of this other paper, where we do is preserve the decreasing characteristic of it, okay? But with a different rate. And then with a rate that can capture as many as you like, in brackets, groups. And if you do that, then you don't need to do that what you're saying, right? You don't need to do that.
You're saying you have a rate that's slower than the geometric of the decay?
Yeah, exactly.
Okay.
So this paper goes a bit on that discussion, and it's about to be done, I think. We are just, don't look at the mistakes, right, please? So these are, for instance, different kind of decays, right? Different decays. You have the geometric, and you have the negative binomial prior. So you're changing, but that you get that kind of you get that kind of point. But that's an important point, because if you, and that's Michele was asking me before, because for those who tried this before, and that's why I say it goes with a price, right? So essentially, the Dirichlet process is while, but you just put a prior. But it's not true because you have to tune a lot of the parameters. Otherwise, you don't get wherever you want to get, right? For real non-parametric problems. Of course, if you wanna estimate 3 modes, whatever, it's gonna be easy, right? But for this model, you only have 1 lambda, so everything goes into that. And if you saw the asymptotic results change a lot when you change the prior. So that's telling you that it's very sensible to that. So you have to be creative in that. And if you ask me, we haven't been enough creative in doing that. There must be a way to do that for very complicated problems, right? To make it like online kind of process that doesn't need any input right from that. So we haven't done that, but I reckon it could be possible, right? As in the Dirichlet cases, which is also messy, right?
Other questions?
Comment. I had a former colleague where I used to live that used to say the problem with Bayesian statistics is that it's too simple. So somehow you have to be careful how you say that in certain crowds. And anyway, this is obviously not simple to the rest of us, but it's simple to you. Comment, or another, I guess you answered part of my question just now with Eric's question, but so when you prove the support properties using the exponential, then what you're saying is that that's going to depend, you're going to have a proof of that depends on the class of priors that you put on this parameter that you're talking about.
Yeah, that's right.
So everything works out, but the devil's in the details.
But that's a good question. It's also the same with the when it's not the Dirichlet because you call it already Dirichlet, but this is just a model. But if you change the B's in the stick breaking, also the properties change, right? The support properties.
Yeah.
So it is the same
Yeah.
It goes along with that, right? So, but of course, I mean, if you change that, you change the support properties. But all of them are weakly full support in the weak consistent, the weak topology, right? So essentially, you have the same support of having all distributions in that particular rate, weakly speaking, right? And we haven't been able to prove it in a different sort of topology, but it might be possible, like they did with the Dirichlet later, right? So, but the point is it depends on the prior, as it does with the completely random measures. It depends on if you want to call it like very deeply into the mean measure of the completely random measure. You change that, and the support is completely different, right? So, but I insist, right? How can you get? I mean, if you are not a Bayesian statistician, if you are not a Bayesian Nonparametric guy, how can it be simpler than just explaining? I knew it would be difficult. This, right? I mean, there is nothing simpler than this. Forget about all the maths I told you, and just think about this. It's random locations in a geometric sort of way.
I agree.
I mean, it's super easy, right?
I agree. Some of the other slides were a little more complicated.
That's right.
And since nobody laughed when I said that first thing, this is a really stupid thing for somebody to say. The problem with Bayesian statistics is that it's too simple, even when it is simple.
Yeah, it is simple.
I've had papers rejected because they were too simple.
That is right.
That are among my highest cited papers in another journal, of course.
That is right. I completely agree on that comment.
Anyway, so
The simpler,
simple is
the
good.
easiest, and the nicest.
Perfect. Let's thank again Ramses.